Dear students, in this class I will discuss about electric field lines. Let me move on to discuss about what are electric field lines. Here, electric field lines are the imaginary path along which a unit positive charge moves. That means, suppose if you consider this as a region of electric field. See, if this is the region of electric field, suppose if we put a unit positive charge, we know already electric field is produced due to a source charge. So here is some source charge. So due to that, so there is a field region around it. Suppose if we put a unit positive charge nearby it. So this unit positive charge either attracted towards this source charge or repelled by it. It depends upon the nature of the source charge, right? So due to the attraction or repulsion, so it will move, it will start to move. So along which path it starts to move, that imaginary path will be called as a electric field line. That's why we say electric field lines are the imaginary path along with a unit positive charge moves. And in another way, we can also say the electric field lines are the curved paths. These are the curved paths such that at any point of that path, suppose if this is a curved path, so electric field line is a curved path such that at any point on that path, if we draw a tangent, so then that tangent gives the direction of the electric field at that point. Suppose if you draw a tangent at this point for this curved path, then the direction of electric field is so this one at this point. If you draw a tangent here, the direction of electric field at this point is like this. So the definition of electric field, so in another way as it is a curved path such that at any point on that path if we draw a tangent, that tangent gives the direction of the electric field at that point. Now let me move on to discuss about the basic properties of these electric field lines. In that, the first basic property is the electric field lines always starts from positive charge. Starts from positive charge means the electric field lines started to move or originating from the positive charge like this, and always terminating at the negative charge means they start to move from positive charge and end at the negative charge. So we say electric field lines start at positive charge and ends at the negative charge. That means they are originating from the positive charge and terminating at the negative charge. So this is one of the basic property. And the second property is these electric field lines do not form closed loop. They do not form closed loop. How we say they do not form closed loop? See, go to the first property. I have told you electric field lines start from positive charge and ends at negative charge, right? That means electric field line do not, if they start from positive charge, they do not return to the positive charge again. They ends at negative only. So they start from positive and go away. Okay. So that's why they do not form closed loop. That means they do not return again to the same charge. That's why we say the electric field lines do not form closed loop. And the third property is two field lines never intersect with each other. That means if we consider any two electric field lines, they do not intersect like this. It's not possible. Means the electric field lines do not cross with each other or intersect with each other. Why they do not intersect? Suppose what happens if they intersect? See, suppose if the two field lines intersect with each other, at the point intersection. According to this definition, means the tangent drawn at any point of the field line gives the direction of field, right? So, if we draw a tangent at this point for both the field lines, see here we can draw a tangent to this field line also and tangent to this field line also. See, we are having two tangent for a single point. That means there are two directions of electric field for the same point. It is not possible to have a single point, the two directions of electric field. That's why the two field lines do not intersect with each other. And the fourth property is, if we consider a charged conductor, the electric field lines are always perpendicular. If this is the electric field line, so electric field lines are always perpendicular to the surface of charged conductor. So we can say the electric field lines are always normal to the surface of the charged conductor. If this is the charged conductor, then the electric field line is always normal to the surface of the charged conductor. See, if it is a positively charged surface of conductor, then electric field is acting outward from it but normal to it, means perpendicular to it. Suppose if this is a negatively charged conductor, the electric field lines are acting inwards but it is normal to the surface of the charged conductor. So these are the main basic properties of the electric field lines. Now suppose if we consider a single positive charge. In the case of a single positive charge, the electric field lines are always acting radially outward. See, the electric field lines are acting radially outward due to a single positive charge. Means charge is greater than 0. Okay. Suppose if we consider a single negative charge. In the case of a single negative charge, the electric field lines are always acting radially inward. See, this is in the case of single negative charge. Okay. So these are how we draw electric field lines in the case of a single positive charge and in the case of a single negative charge. What happens if we consider two like charges? In the case of two like charges, how do we draw the electric field lines? Let me move on to discuss about that. See, suppose if we consider two like charges, either two positive charge or two negative charges. Okay. So, in the case of like charges, the field lines produced due to both the charges exerts lateral pressure, means sideways pressure on each other. That's why there exists a force of repulsion between those two charges. Means if this is the field line produced due to this positive charge and this is the field line produced due to this positive charge, these field lines exerts lateral pressure on one another. That's why the two charges will move away from each other. So we say like charges will repel. Okay. So now we can draw the field lines in the case of the two like charges, means two positive charge like this. In the case of positive charge, field lines are moving away, right? So this is the representation of schematic representation of electric field lines due to like charges. In the case of like charges, product of the two charges will be always greater than 0. Then, in the case of negative charges, these are also like charges, two negative charges. So, here also the same thing, there exists a lateral pressure between the field lines produced due to both the charges. Okay, that's why the two charges will move away from one another. Okay, but only the difference is here the field lines, so moving towards these charges, here field lines are moving away from these charges. Okay, suppose if we consider unlike charges. Then how we represent the field lines, how we draw the field line. In the case of two unlike charges, so those two are those two are not the same kind of charges, one positive and one negative. In that case, the product of two charges is always less than 0, that means negative. In this case, there exists a lengthwise contraction between the field lines produced due to both the charges. So here how do we represent? That's why due to the lengthwise contraction due to the field lines produced by both the charges, the two charges will move towards each other. That's why the two charges will attract. Okay. So, how do we draw the field lines due to these unlike charges? Here, the field lines start from positive and ends at the negative charge. So, we represent the field lines due to unlike charges like this. Okay, this is the representation of the field lines due to unlike charges. See? At negative charge, field lines are terminating. They are ending at the negative charge, and they are originating, means starting at the positive charge. This is how do we draw the field lines due to unlike charges. Okay. So, electric flux. What is electric flux? Electric flux means it is the total number of electric field lines that are passing through the surface. If we consider this as the surface, see, this is the surface. So then total how many number of field lines are passing through this surface if the surface is held perpendicular to the direction of electric field. See, this is the electric field direction, and if this is the surface area, and so the surface area is held perpendicular to direction of electric field, total how many number of field lines is passing through it, that is called as the electric flux. That's why we say total number of field lines that are passing through the surface area which are held perpendicular to the direction of the field lines. And this electric flux is a scalar quantity. Electric flux is a scalar quantity, and its SI unit is Newton per Coulomb meter square, or simply Weber. So, this is the SI unit of electric flux, and it is a scalar quantity. Now, let me discuss electric flux due to area element. If we consider one small, it's not possible to consider the whole area and calculate the total electric flux. For that, let me apply this concept to find the electric flux. So, to discrete value means a small element. So, for that, let us consider a small area element. See, consider this as a surface having area S. We have considered a surface of area S. In that, we have considered a small area element which is having the area as delta S. See, if we draw a normal to this surface, the normal is like this. This is the normal. Here, we are considering the area in a particular direction. That's why here we treat this as a area vector. Okay. Suppose if the direction of electric field at this surface area is along this direction. Now, how do we find the total electric flux or electric flux due to this small area element? Okay. Now, let us consider this normal makes an angle theta with the direction of electric field. Okay. So, now the electric flux, consider the widest view of this. Here we have taken the small area element of area delta S, and if we draw a normal to this surface area, normal means perpendicular, this is the normal drawn to the surface area element, and this normal is making an angle So theta with the direction of the electric field. Right. So now, how do we write the expression for electric flux? So this is the area vector, right? Now resolve this area vector along the direction of electric field. If we resolve this, here is the angle theta and this electric field is adjacent to this normal. That's why, since it is an adjacent to this area vector, the component of this area vector along the direction of electric field is delta S cos theta. We have to consider the area element along the direction of electric field only. That's why the element, the component of area vector is delta S cos theta. Okay. So if you resolve, here we get delta S sin theta. But so we didn't use this delta S sin theta. We need only delta S cos theta because this is the component that is acting along the direction of electric field. Now, the electric flux is given by the electric flux passing through this small area element delta phi is given by, see, this delta S cos theta. The flux that is passing through the area delta S cos theta into the field at that area is E. Now, here we write delta phi is equal to E delta S cos theta. Now see, this is in the form of AB cos theta, product of magnitude of two vectors and cosine of the angle between them. That is nothing but scalar product or dot product, right? So, we write delta phi is equal to the dot product of vector E and delta S vector. So, we can also define the electric flux as the electric flux is the dot product of electric field vector and area vector. Scalar product of electric field vector and area vector. Okay, that's why we say, so this flux is a scalar obtained by the dot product of two vectors. Okay, so now, so how do we find out? Suppose here we are finding out the flux due to the small area element. Suppose if we consider the entire area of the surface. So if we consider the entire area of the surface, then we have to sum up the flux due to all those small area elements. Okay. Therefore, the total flux due to the whole entire area is given by phi is equal to summation of delta phi for all area element. Okay. Or, so this summing process is, if we use a summation process, that is a long process. That's why we use a special type of summation that is called as an integration. That's why the flux is the line integral of vector, delta phi, that is nothing but vector E dot vector delta S. This is how we find out the total flux. Okay. Then, so by using, if we know the value of electric flux, that is delta phi, we can find out the value of electric field. How do we find out the value of electric field? So for that, let us consider delta phi is equal to E into delta S cos theta, right? So if you want to find out E value, now take this delta S cos theta to this side, it will comes to the denominator. Therefore, the electric field E is given by delta phi divided by delta S cos theta. That means electric field can also be defined as the flux per unit normal area. Okay, it is the flux, electric flux per unit normal area. Suppose if theta is nothing but angle between the area vector and the field vector, right? So angle between the normal and the direction of electric field. Suppose if these two, if electric field is along the normal, then theta becomes equal to 0 degree. If theta is 0 degree, then cos 0 value is 1. So now substitute this, we get E is equal to delta phi divided by delta S. Here cos theta value is 1. That means electric field can be found by using the expression delta phi by delta S. Okay. When does this electric flux is maximum and minimum? Let us discuss that. So for that, again consider the expression for the electric flux, that is delta phi is equal to E delta S cos theta. Here the expression for flux is known to us, that is delta phi is equal to E delta S cos theta. Right. Suppose if we consider, if the normal drawn to the surface is along the direction of electric field, if the normal drawn to the surface is along the direction of electric field, then angle between them is, see, both the normal and electric field, both the area vector and electric field are acting along the same direction. We know if two vectors are acting in the same direction, the angle between them is 0 degree, right? So here theta is 0 degree. If theta is 0 degree, then cos 0 degree value is 1. Now substitute this value in this expression. Therefore delta phi is equal to E into delta S. Cos theta value is 1. That means flux is maximum. The electric flux is maximum. So we say if the electric field direction, if the electric field lines are passing along the direction of normal, then the total electric flux is always maximum. Or if the electric field direction is along the normal, then flux is maximum, and the maximum value of the flux is given by, so delta phi is equal to E into delta S. Okay. So now, suppose if the normal drawn to the surface is perpendicular to the direction of electric field. Now see, this is the normal, perpendicular, that is drawn to the surface, and if this normal is perpendicular to the direction of electric field, means the electric field direction is here, then angle between electric field and the normal is 90 degree, right? So then if theta is 90 degree, cos 90 value will be equal to 0. Cos 90 is 0, right? So delta phi is equal to E delta S. Cos 90 value is 0. So into 0. 0 multiplied by anything is 0. See here, flux is 0. That means the total electric flux is minimum. That's why we say if the electric field is perpendicular to the direction of normal, then flux is minimum. If the electric field is along the direction of normal, then flux is maximum. So this is how we find out the maximum and minimum value of the electric flux. Now let me move on to discuss about the next concept, that is electric dipole. This is important, electric flux. So by using this concept of electric flux, so now we discuss the Gauss law and applications of Gauss law in the next classes. Okay. So now let me move on to discuss about the electric dipole. See, the word itself says dipole, means two, right? That means electric dipole is a set of two equivalent opposite charges. A set of two equivalent opposite charges separated by a small distance between them. That is called as an electric dipole. Did you got this? Electric dipole is a set of two charges which are equal in magnitude but opposite in kind. Okay, that is called as an electric dipole, and those two charges are separated by a small distance. And the distance of separation between the two charges in a dipole is called as a dipole length. Okay, Dipole length means it is the distance of separation between the two charges in a electric dipole. And this dipole length is always acting from negative charge to positive charge. So, the direction of dipole length is always from negative to positive charge. So what is the net charge? I mean total charge in the case of an electric dipole. The total charge in the case of an electric dipole is always equal to sum of the two charges in that system, right? So that is plus q and minus q is nothing but 0. So the net charge in an electric dipole is always equal to 0. Now let me move on to discuss about the next concept, that is dipole moment. What is dipole moment? If we consider a dipole, we know it is nothing but a pair of equal and opposite charges separated by a small distance between them, right? So dipole moment means it is the product of one of the charge in a dipole and the dipole length between the two charges simply. And this dipole moment is represented by the symbol P. So the dipole moment is defined as the product of one of the charges in a dipole and the distance of separation between the two charges in that dipole. The distance of separation between the two charges in a dipole is nothing but dipole length, and any charge magnitude is q. So dipole moment is given by P equals to q into 2a. And the SI unit of dipole moment is coulomb. Charge unit is coulomb and dipole length unit is meter. That's why the SI unit of dipole moment is coulomb meter. And this dipole moment is a vector quantity. It's a vector quantity. So, we can write the expression for dipole moment in vector form as vector P is equal to Q into 2A into P cap. Here P cap is a unit vector that is acting along the direction of dipole moment. And what is the direction of dipole moment in a dipole? The direction of dipole moment is always from negative to positive charge in a dipole along the direction of dipole axis. Okay. So, direction of dipole moment is always from negative to positive charge along the dipole axis. Then, suppose if we consider, let us discuss about some definitions related to this dipole moment. If we consider an electric dipole, the midpoint between the two charges in a dipole is called as a dipole center. The center point between the two charges in a dipole is called as a dipole center. The line that is passing through the center of the dipole along the axis will be called as a axial line. This will be called as a axial line. And the line that is passing perpendicular to the dipole axis through the dipole center will be called as a equatorial line or bisector line, because this line bisects or divides the two charges in a dipole equally. That's why we say it as a equatorial line or bisector line. Equatorial line or bisector line. Okay. Now this is about the electric dipole, and in the next class I will discuss about the expressions on the axial line and equatorial line for the electric field of a dipole.